Good afternoon, everybody. Um, my name is Madeline, and I'm going to be presenting on soils today with Robert. We're really excited. Thank you for spending your Saturday with us. I know it's the weekend, um, and it's pretty beautiful outside, so I would like to keep this under the time that we are allowed for this so that we can all kind of carry on with our day. Um, so, hello. I'm going to get this. I think you guys can see my screen here. Please let me know if there's something wrong here, but yeah, thanks for joining us today. I'm really excited. This is my first, both Robert and my first year working with folks for Envirothon. And I think it's super neat, especially with the topic that it's around. And I'm pretty passionate about soils. And so I'm excited to share all this with y'all. I'm sure a lot of this first webinar here, this is one of 3 that we're going to be doing over the course of the next month or 2 leading up to the competition in April. And I'm sure a good amount of today's content will just kind of be a refresher. But yeah, let me see here. At the bottom of the window. Okay. Does this look good, Robert? Is it in?
It's still just showing the editing screen, the original slides.
Really?
Yeah.
Right. That's great. Okay. I don't know how to present it. Start from beginning. Weird. Okay. Well, I mean, I guess we could just like do it like this. That works. If anybody's.
They'll just have to deal with the spoilers of the next slide.
Yeah, right. Okay. Well, here we go. Alrighty. So I'm Madeline. I work with the NRCS. The field office I work out of is in Petaluma, California, which is Northern California, and I am the soil scientist for the office up there, as well as a recent hire soil health specialist for Area 2 in Northern California. And that area covers counties ranging from Goldridge down to Marin, Humboldt, Sonoma. So it's a really beautiful area, and I'm really lucky to be up here. I actually just moved from Colorado about a little over 6 months ago, and loving the greenery out here. It's pretty dry in Colorado. I don't know if anybody spent much time out there in this group, but yeah, I'm loving it a lot. And Robert, would you like to introduce yourself?
Yeah, so I'm Robert. I'm also a recent hire soil scientist focusing on soil health. I'm responsible for Area 4, which covers most of Southern California. I'm actually located by the Salton Sea down in Imperial. It is an interesting change for me. I moved from the East Coast. I'm from Tennessee, and essentially I'm not used to the desert, and it's been a wonderful change.
Yeah, I feel like this area, I don't know if down there is as much transplants, but this area, there's not a whole lot of transplants that I've noticed in Northern California. A lot of folks have been here for a while. Anyway, so our agenda today, I'm gonna walk with y'all through just some, like I said, probably a bunch of this is some refresher stuff, but refreshers are good. I'm gonna try to keep it pretty light. Just talking about soil forming factors, processes. I'll talk about a couple properties, and then most properties Robert's gonna walk you through, and then we'll finish up with just talking about some basic horizon information and how to look at soils in that kind of way. Feel free to raise your hand throughout if you've got any comments, or, we don't have to wait to the end for that. I'm not looking at the screen though, so if you see anything, let me know. But yeah, so soil, the technical term, the top layer of the Earth's surface containing unconsolidated rock and mineral particles mixed with organic material, but really it is just looked at as a medium for plant growth. It's kind of measured in that way. I don't know if anybody's ever seen the documentary Symphony of the Soil. It's a good one. Deborah Coons Garcia said that soil is the essence of life, and she is quite correct, because almost all life on Earth depends on soil, either indirectly or as a direct source of their of how they survive. I mean, we're alive because of soil, plants grow because of soil, animals are alive because of soil. And a couple of fun facts. Soil is crazy awesome when it comes to biodiversity of microorganisms. I mean, I think that the most biodiversity, the most amount of organisms in any kind of terrestrial biome or ecosystem or type, it is within soil. Also, it takes forever to form. So 10 millimeters of soil can take up to 1,000 years to form. And that's a teeny tiny bit of soil. I like this photo on the right side at the bottom. It's just, I think, a pretty picture of different microorganisms that we find in soil, different fungi, bacteria, nematodes, all the fun ones. Oh, and just some morphology here, but I'm sure you guys know a bit of that. But okay, so 5 soil forming factors are parent material, which is more of an indirect one, but super important. Some parent material weathers faster than others, and this really decides the type of soil that it's going to be ultimately. A super important forming factor, organisms or vegetation. This is a more active factor. And the kind of ecosystem that you are in really decides the soil type as well. So if you're in a prairie ecosystem, that those grass roots and grasses are going to contribute to the soil structure and what that soil horizon, that profile looks like. And same if you're in a boreal forest, it's just going to look a lot different. And those needles and leaves, that kind of litter is going to really contribute. The kind of the kind of vegetation also, I think, influences the microorganisms within the soil itself, which determines the rate of decomposition. So that's a big one. Topography, the actual shape of the landscape, slope, position, all that really determines how much of external factors are going to be affecting the soil. So how much is lost to erosion and runoff, how quickly a lot of that weathers. And so soil on the tops of hills tend to be deep, and soils in valleys tend to be deep, and soils on the side of hills often tend to be a bit shallower because of that steep slope. Our fourth soil forming factor is climate, huge one. Temperature and precip, big weathering effects on the soil. Different soil if you're in the Arctic or in a tropical region. And that is also an active factor. And our final soil forming factor, which is probably the most important, well, they're all important, but time, because as we know, it takes so long to create one little itty bitty bit of soil. And they're dynamic, so they're always changing, and they're changing both in their chemical properties and their physical properties. And yeah, so a change in any of these 5 soil forming factors, I mean, there's infinite combinations, right? Like type of climate, how much time, what kind of vegetation, infinite combinations, which means an infinite amount of soils. And that is very true. So factors are great. Factors often is what determines the processes. The forming factors determine how a soil is going to really react, or what's going to happen within that soil, and how it's going to react to things being added or lost or changed within it or outside of it. So there are several soil forming factors. We're going to focus on just four. There's four main ones. Additions, so things coming into the soil, both from above and below. So, leaf litter, rainwater, chemicals, fertilizer from agricultural activity, and also from below, like capillary rise, nutrients, dead roots. And the second process is losses. So basically the opposite. These are losses out of the soil, out of the soil itself. So things lost due to transpiration, right? Runoff or erosion. It's not staying within that soil, it's leaving it outside of the soil entirely. I like to look at this, an example is the plants taking up nutrients and those plants being harvested and consumed or fed to livestock or anything, and those nutrients are lost from the soil. Translocations are similar to losses because it's movement, but this is internal movement within the system, the soil system itself. It's just moving from one area to another. So this is when, like, illuviation from an E horizon, which we'll get into more later, but I'm sure y'all know about soil horizons and how B, there will be elements leaving B that accumulate into the E horizon. It could be leaching of organic matter, clay, minerals, and other nutrients from one horizon or one part of the profile to another. And the biggest, transformations is huge. It's just big processes because this is internal changes, and this is just such a broad thing. So all the colors that we see in soil when we're looking at an aggregate or clod, and we see these redoxes here on the right. These are some redox is reduction in oxidation, and it's from lack of oxygen. And so a lot of times nutrients or chemicals, minerals will accumulate all in one place, and they will create these beautiful marbling of colors, maybe not always the best for plant growth, but some plants do okay with it. Other transformations, how organic matter is transformed into accessible forms of nitrogen for plants to use. And it's transformed by microorganisms. They're decomposing that. They're making it readily available for plants. Other transformations could be the transformation of the structure itself. So let's say livestock or human activity, foot traffic, tractors compacting the soil. You're altering the pore space within a soil profile, and that is transforming the structure. Other things like feldspar weathering into a clay mineral and all that. So transformations are pretty huge. And oh yeah, this up here just talks a bit more about redox. And this photo here was taken by John Kelly's Flickr account. He has worked with folks and worked for the NRCS, and he's got some great, I should have included his Flickr account on here. Maybe if anybody wants it, let me know. It's filled with just gems of photos like this. So many pictures. All right. So I guess we can move on to soil properties. Does anybody have any questions this far? I feel like I just moved through that really quickly. But okay, cool. All right. So we will start with a little bit of bulk density, and then I'm going to hand it off to Robert to finish up these properties. I might be biased, but I love bulk density. I think that it is the most important. It's not the most important property. I think it's super cool. It's an indicator of soil compaction, and it really tells us, it can be an indicator of a lot of things. It can really correlate to things like infiltration rate, or it's or aggregate stability. But I guess everything kind of relates back to aggregate stability, but we'll get there. Bulk density is the weight of dry soil in grams divided by the volume of dry soil in centimeters cubed. And on the right at the top, this this bunch of soil particles or aggregates, with these pore spaces in between, looking all healthy, has a lower bulk density than this compacted soil here. There's no pore spaces, there's no airflow, there's no flow for allowable space for nutrients or water to flow. It's got a higher bulk density. Um, a higher bulk density is generally, it's hard for roots to grow. So, plants don't usually grow as big and lush and wonderful in compacted.
Looks like we might be having some technical difficulties. So essentially, the bulk density is going to be one of the main factors that stops the plant's roots from being able to access nutrients further down. Um, Let me get a copy of that PowerPoint up so we can continue where we were.
Okay. Did something happen?
Yeah, I think your PowerPoint went down. Your computer might have frozen. Did you want to put yours back up,
Oh
or do you want
no.
me to take over?
Yeah, I can get it back up here.
Okay,
Unless, do you have a way of bringing it up and putting it into like presentation mode? I don't know.
let me see what I can do here.
I feel like I'm missing something.
All right, we're
Hey.
gonna fast forward real quick, everyone. And we're in our properties. I think this is where we left off with bulk density. So essentially, what really influences bulk density the most is going to be how well those aggregates are formed. A well-formed aggregate is going to have more pore space in it, and a poorly formed aggregate is going to be more compacted, and it's going to affect more of the properties of the soil. The depth of the soil really does determine the bulk density. The deeper you go, the more weight is applied to the soil, and just more compaction that you see over time. Soil's texture plays a huge part in how dense it can become. Sandier soils have larger pore spaces, but fewer of them, and it makes it more difficult for it to aggregate together. So those finer soils like silts and clays are going to be well suited to holding each other together. So that really results in sand having a higher bulk density across the board. So the different management styles that farmers and producers may have used on their land can really determine how well that soil is able to form. So if we till and we plow and we break up the aggregates, it makes it so the soil compacts more easily, increasing that bulk density over time. Again, that disturbance history, it's not only farmers, there could also be natural disasters that come through, flooding and things of that nature, that could increase the bulk density over time. A great way to bring that bulk density down is by adding or allowing organic matter to build up in the soil. It is a fluffier and lighter substance in the soil, so it can help to make it more porous. There's many factors that do influence the bulk density over time, but truly the ones that affect pore spaces have a direct influence on bulk density. So now we're going to move on to soil texture. Essentially, texture is the proportions of sand, silt, and clay, and essentially the percentages. Now, those particles are measured in millimeters, the largest being sand, which is anything between 0.05 millimeters and 2 millimeters in size. So it's the largest particle. Silts fall right there in between, where anything from 0.002 millimeters all the way up to that 0.05. And then clays are going to be our smallest particles, which allows them to ironically have the most surface area. Now, there's many different soil textural classes, and we use them to more easily explain the distribution of these sand, silts, and clays within the soil. The perfect soil that everyone would love to have is going to be a loam, and that's a nice even mixture of a sand, silt, and clay. That's not seen very often, but you might see things that are more like a silt loam or a clay loam out there, and those are still very great soils. Now, interestingly, when we do classify soils, we give them names that allow you to know what is the major component of the soil. So for instance, a sandy loam, the major component is going to be the sand with the, I apologize, I got that a little mixed up. That last type of the particle is our predominant. So that sandy loam, that loam is going to be our predominant, where the sand is going to be the secondary. And vice versa, in a loamy sand, that sand is going to be our predominant and the loam is the secondary. So you could imagine it would be a loam with a higher sand content overall. Now, we have nice abbreviations to help with shorthand when we're out in the field identifying or conveying to others what we have on the ground. So essentially, we use shorthand, S for sand, C for clay. You guys can kind of see where that's going. We also have some modifiers to let you know if there's going to be larger particles of sand in there or finer bits of clay. So we use those coarse, fine, and very fine modifiers to really drive the point home. If you guys felt like quizzing yourselves, you're welcome to type it in the chat or just write it down on a piece of paper. You can use this list. I'll give you about 1 or 2 minutes to see if you can figure out what those textural classes, the VFSL, the COSL, the FS, and the SICL, what those textural classes might be.
Hey, Robert, do you mind if I jump in really quick?
Yeah, of course.
I just wanted to say, all these shortened, when you're out in the field and let's say you're describing a soil pit, if that ever comes about in your future careers, you often have to, things are often shortened into these things. So this is just a little bit of practice of how to read something like that. If you were given, if you were given a short amount of time and or something to read and, explain, right, how many cobbles or rock fragments are in and then you see SIVFSL and, and you don't know too much about it. It's just good to know how to read it. That's all. Also, on the right side, I don't know if anyone's ever done that before, but it's a way to test texture in the field. It's called a ribbon test for texture. So essentially, you just kind of rub you get some soil, you get it wet, and you kind of rub it with your thumb and your forefinger to try to form a ribbon. And where it breaks along that ribbon line, like how many inches in it breaks off, helps you to determine how much clay is in your soil. I don't know the actual, it's more of like it's more visual for me when I'm doing it. I don't know what the exact inch uh, determination is, but it's a useful test. And that paired with the textured triangle are pretty useful in the field when you're trying to determine what this texture is of the soil you're working with. That's all.
Yeah, and I think if it's below 1 inch, you've got a very low clay portion. If it's between 1 and 2 inches, you're going to be more in that moderate amount. And if you're able to get a ribbon longer than 3 inches, you've got a clay predominant soil you're dealing with.
That's right. Thank you. Yep.
Oh, of course, it's a fun one to get your hands dirty with. All right, we're going to move on. I believe cation exchange capacity is next. Now, it's a very important factor when looking at soils. Essentially, it's going to be how well a soil can hold on to positively charged cations and release them to the plant when it needs them. Some of these more common cations that you would see in soils that we have in most agricultural nutrients are going to be things like calcium, magnesium, iron, and potassium. Salt is also a cation. So these cations, they all have a charge, and that charge strength is really how well or strongly they bond with the soil itself. So something like iron is going to be a bit harder for the plant to access than maybe potassium. So that potassium will be traded off more often and easily. Something that really helps to determine the amount of cation exchange capacity is going to be the amount of organic matter and clay present. They both have a very high amount of negatively charged particles on their surface. So clay loam or with a good amount of organic matter is going to be a lot better at holding nutrients and offering it to the plants than a sandy soil with no organic matter. So soils with a high CEC, like I was saying, are better at holding nutrients and exchanging them for the plants. Soils with that lower CEC tend to be less fertile and not as advantageous for crops and things of that nature. CEC is really determined by the soil's pH, and soil's pH is going to be the measure of acidity. I'm sure this has come up once or twice in a chemistry class for many of you. The 0 on the pH scale is going to be our most acidic, and 14 is our most basic or alkaline. Now, for agricultural purposes, most crops like a neutral pH, somewhere between that 5.5 and 7.0 range. Nutrients are just more readily available to the plant in that range. Now, most soils, I mean, they range from slightly acidic to slightly basic. Those acidic soils are better for crops like blueberries and things like that, where the more basic soils are going to be plants that aren't needing as much nutrients as frequently. The solubility of minerals really helps to determine how are really dependent on the soil's pH. A more soluble nutrient is going to be accessible to a plant at that neutral pH. It can also influence how well the microorganisms in the soil are able to reproduce and make available nutrients for the plants. Bacteria is a big decomposer of organic matter, and if the soil's too acidic or too basic, it stops the bacteria from being able to do its job, and it results in a very large amount of organic matter in your soil that does not break down over time. So you get a very dense layer of inaccessible nutrients. The image we have over there, you can kind of see where that sweet range is in the center, where most plants enjoy things. As you can see in the alkaline end, some of those elements are going to be a little bit less available to the plants, and those are micronutrients that they are just as necessary for the plant to live as the big major ones, nitrogen, phosphorus, and potassium. Now, soil porosity is a fun one. It's essentially how well the soil can act as a sponge. A soil with more porosity is going to have more airspace, which can be used to exchange gases, water, nutrients, all of that great stuff. The soil's texture, like we were talking about, really determines the amount of porosity. Those clay soils, because they're finer, are going to have a little bit less pore space between them because they stack on top of each other. Where sand, having a larger size particle, is going to have more airspace between each other. So that really just means that it can hold more water, more nutrients, more oxygen, all of that stuff. The compaction is going to influence the pore spaces as well. If we have a very heavily compacted soil, it's going to press all those pore spaces together, and it's not going to be as advantageous for plants and everything else. Those microorganisms, they do use the space between all of the soil particles as a home. And so in that compacted soil, it's just not going to give them the advantage that they would need. The roots, they travel through the pore spaces. So a more porous soil is going to let the roots move further and more widely than a compacted soil. Now, the gas exchange really is one of the more important parts. You don't want to have a soil that is full of water, very little pore space, and the plants are essentially sitting there drowning without any oxygen to access. So that is one of the big factors, pore space effects, is how much oxygen and gas is in that root zone. Soil color is a very interesting property. It's a great way to understand what the parent material of the soil is, maybe how well the soil drains or how often it's saturated. You can even use it to help determine the amount of iron and organic matter in the soil. Generally, well-drained soils are going to be brighter in color, and darker soils are going to usually have more organic matter. So an interesting thing that happens when soils are exposed to water for long periods of time, you get what's called glaying, and it's actually when the soils start to turn gray or even blue in color. Well-drained soils obviously are going to have more of a dark brown color to them, and sometimes you might even find mixes of colors where there's small bits of colors within a main color, and those are going to be more like splotchy and interveneous. We call those molts. Essentially, when we're out in the field, we use a color chart that is going to be a consistent color for everyone everywhere. We use the Munsell color book. It's like I said, pretty standard across the United States. We look at things like hue, value, and chroma. That hue is going to be how much red, yellow, or blue is in there. We use, again, easy shorthand, R for red, YR for yellow, red, G for greens, that kind of stuff. Now, the value is going to be how light or dark that hue is. You might be able to see on the picture, the chroma is on the bottom of the page and the value is on the rise of the page. So we use that to match up with the page on the left. You can see some of those brownish yellow colors in the middle, like the 6.6 and the 6.8. That would be a value of 6 and a chroma of either 6 or 8. That chroma is going to be how weak or strong the color is. So it's really going to help us know if it's a darker chroma being that 8 or a lighter chroma being that 6. It's a very interesting way to compare the soils. It's kind of fun to get them wet, hold them behind there, and kind of play a matching game to see if you can find the right color. And then finally, I believe we're getting on to aggregate stability. That's something we've touched on a handful of times, and a lot of the soil forming factors do affect The aggregate stability is really how well the soil can hold itself together. It regulates the water movement, the air movement, all of that through the soil. It provides those habitats for the microorganisms in its pore spaces and the soil nutrients for the plants as well. It does help to improve the soil's drought resistance because it allows the soil to hold on to more water for a longer period of time. It can also help to bring ecosystems together, kind of stabilizing riverbanks and things of that sort. A good way to think of it is an increase in aggregate stability will increase your biological activity, and that would also increase your plant's production and root growth. So it's good to have a stable soil. Again, the things that all influence your aggregate stability are things we've kind of been touching on the entire time. Is that texture, how well your climate and other forming factors are affecting the soil, how much you disturb it, and then how much organic matter's in there. I believe our soils on the right, you're going to see a very stable soil, both in the gentleman's hand and with the plant roots all throughout it. You can see how well that soil's held on by the roots. And then that large aggregate that he has in his hand is going to be a good way of seeing how the below ground soil is holding together. Now, the soil below it is very poorly formed. It has a very weak structure. It seems to have crumbled under very minimal pressure. And that's not going to be good for water. It's going to break apart and erode more easily. It's not great to see. Organic matter is another thing we're going to touch on. Essentially, that's going to be another component of soil apart from the main three mineral components. It's going to be consistent of dead and dying plants, animal residues, and other materials which can be converted by microorganisms to nutrient and available sources for the plant. It has direct influences on bulk density and aggregate stability. It increases the ability of the soil to hold water. It can increase those pore spaces and help increase the flow of air and water through the soil. Generally, it is going to decrease in soil depth because it builds from the top down. Sometimes there are some instances where you might find a buried organic horizon where something like a landslide or agricultural work has been done. And so you might find a secondary darker horizon down low. Organic matter really does increase the productivity of a soil. It allows for a lot more nutrient exchange because of that increased cation exchange capacity. And healthy soils usually will have stable levels of organic matter, and they're better equipped to fight soil-borne diseases, droughts, all of that kind of stuff. A healthy soil is a happy soil. I think in our image over here, we're going to have some of the forming factors for organic matter. You're going to have that plant residue, that animal ingesting the plants and leaving its residues as well. And then in the soil, you're going to have organisms like earthworms. Yep, I'm spacing on any other ones. Nematodes, things of that nature, breaking down the deposits and making them available to plants over time. I think Maddie's going to step in for the soil horizons.
Yeah, thanks, Robert. So soil horizons. I love this part. I think that the soil, looking at the soil profile is the coolest part of being a soil scientist and being able to look at all the distinct mineral and chemical accumulations and the colors. I find it really beautiful. So there are 5 main horizons. I included E in there because I also think that E is a main horizon. I am from, well, I'm not from Colorado, but I lived in Colorado for about 8 years, and you find a lot of those kind of horizons in the kind of forests that we have up there. It is it's a concentrated layer of leached material, and there's definitely soil out here in the West in California that includes the E horizon as well. So I think we should include it. So the first horizon is the O horizon. It's the organic material accumulated under wet or humid conditions. It is the the litter deposit. It's what feeds the rest of the soil. Underneath that, we've got the A horizon, and the A horizon is the mineral horizon. It's the topsoil layer, and it is formed at the soil surface and includes the decomposing organic matter from above. So an A horizon can be shallow, it can be deep. If you are in a tall grass prairie in the Midwestern United States, you're going to see a really dark, deep A horizon. And these kind of soils, they're called moloch soils. They're called like the breadbasket soils because they're so good. They're so productive. They're really great at growing crops. And but soils that maybe are in a forest ecosystem or a marine ecosystem, a coastal ecosystem, they may not have as deep of an A, or maybe not as dark of an A as a moloch or a grassland prairie kind of ecosystem would. So that's how you can kind of categorize that. I guess that this graphic here on the right doesn't do a good job at showing all of that because it says light in color. It can be light in color. It can also be dark in color. So those two in there, I don't know why those got included, but we can move on. Well, I guess I'll just talk about it while we're here. The next slide talks about the other horizons, but so we next have E, and this is leached minerals, and that often deposits into the horizon below it. It is the E is typically present in forested areas, like I said, and it lies underneath the O and or A horizon. I guess there are soils that skip over the A horizon completely. It's really light colored. It's really distinct. It's white or light yellow or light brown. And it's because it's leached of all of its minerals. And the B horizon underneath is the mineral horizon. We call this the subsoil. And it has been altered by the formation of soil structure. It's generally brighter in color, and it's enrichment and mineral or organic material as well. So this is the zone of illuviation. The E is illuviation. Then we have the C horizon, which is unconsolidated mineral horizon. And it's usually a good amount of weathering. And then underneath that, we've got bedrock. And that's just the parent material, that's rock. Would you go to the next slide? Thank you. So a little bit more of that. I'm sorry, I don't know why I said C is weathered. I meant least weathered because it is so close to the R. I don't know why I said it's mostly weathered. But yeah, so these soils on the right, I believe the one directly on the right, I'm trying to find where that one was. I don't know exactly. That might be the California state soil. Does anybody know what the California state soil is? The winner gets, I don't know, but the winner gets a big hurrah. But it's I think that's the California state soil. If anybody knows it, feel free to put it in the chat. But you can see the difference between soil horizons. So you've got one that is less developed than the other. The one on the left is a bit less developed. It looks like there's a pretty high clay accumulation there. And it has some weak structure. And on the right, we've got a bit, a deeper A horizon and more, it's been more developed. You can kind of see those layers pretty clearly on the right there, and the color changes throughout, which I think is really neat. It's the distinct layers, they're organized pretty visibly in that one, and you can better tell chemical structure. And I tried to include one that had the R, the bedrock, included at the bottom, because not all soil profiles that you're going to be looking at or have looked at or have seen pictures of have the R, the bedrock layer included. A lot of the times, you keep digging and digging and digging, and you don't really hit that. You usually just hit a really deep sea horizon. But I thought this one on the left was pretty cool. Okay, so those all that we just covered, those O, A, E, B, C, R, those are the main horizons, the master horizons. And this part here, I'm going to try to keep pretty brief. And the reason that I included it is so that, when you are looking at a head-on description in the field, or if you have to make one, you will understand what these little letters mean next to the big letter. So next to the main horizon, there are subordinate horizons or suffixes. And they're, would you go back one, Robert, just to the slide before? As you see, like next to these letters here, or the main letters, the A and the B and the C and the R, you've got 1 and 2 and W and T and N and K and Z. And that's, what does that mean? So, okay, we could go back to this subordinate horizon. So this explains it a bit. On the left here, these are some commonly used suffixes. So these were, you'll see, I guess I didn't include Z in there. But if you see a T, it means that there's an accumulation of clay. So if you have a BT horizon, that means that it's a B, B layer with an accumulation of clay. If you've got, a BW, that's a B horizon that has weak development. And these further explain what you're looking at when you're looking at a soil profile. It helps to visualize what each profile is when you're out in the field. There's a lot of different kind of suffixes. There's K in Colorado. Again, they had a lot of accumulation of carbonates out here. There's definitely that. But out here, what I didn't have out there was you do see some G's, some as suffixes, some strong glaying, which is I spelled glaying wrong. It's Gley. I don't know why I did Gleii. But that means that it is, and I like glaying because it sounds like gray, and it is gray in color, and it means that the soil is probably a pretty a not great drainage class. It's pretty waterlogged. H is for histosol. Histosol is higher in organic matter, and so on. And so some examples to the right here. Again, BT, accumulation of clay. AP, that's an A horizon that has been plowed. That one's pretty easy to remember. And we do see that a good amount here in Northern California. There's a lot of agricultural land out here. And so a good amount of that is included when describing a soil pit, especially on land near a dairy or a rangeland, or near even vineyards. And then so you'll see sometimes like numbers next to the profiles, next to the master and then the suffixes. And that's just if there's two horizons that are similar enough, or they both have an accumulation of clay and they're both a B horizon, but they have some differences. whether that's structure or color or rock fragment content. So that's what you will see there. Those numbers probably don't mean as much or need to even be brought up though right now, just as long as you know what these little suffixes mean, because those can be important. Oh, that's it. So yeah, I included this little link here. You feel free, maybe I'm gonna try to put that into the chat, because that is a cool, here, let me get this. That's what I'll do. If anybody's interested, it's a cool, I just put into the chat, it's this cool website where you can kind of play around. On the left-hand side with the 3 lines, you can go down to if you go to the web of soil, I like that one, and you scroll down just a little bit, you'll see all these bubbles appear, and it's fun to play around with. It's what soil makes, you know, it makes clothes and food and fuel, and that will link you to other things. It's just a fun little interactive website to play around with. But that is about it on my end. And Robert, I don't know if you have anything that you'd like
I just
to.
wanted to add that we did send out some study materials. They're going to be a culmination of a handful of videos that we found that do a great job of just summing up some of the major points that we went over. They by no means need to be watched, but if you wanted like a 5-10 minute refresher on what bulk density was, feel free to dive into those videos at any point.
Great. Awesome. Yeah. Thank you for uploading those. Does anybody have any questions about what we went over? I know it was pretty content, just material is pretty heavy.
Let's see,
for the
we've got
first
a
webinar.
couple. Let's see. Carter Yan, I believe you had your hand up first.
Hi, so I actually had 2 different questions.
Sure.
So first, when you were mentioning color, you mentioned models. What causes that in soil formation?
So for modeling, I'm sorry, is that what you were asking about?
Molts, I believe, is
Oh,
what he's
molds?
referring to.
Oh, sorry, I must have
So,
mispronounced it. Yeah.
oh, soil modeling. So it's a color pattern, and it's kind of like this patchy of different colors. And it is currently it's a prolonged, it's the saturation. So when a soil gets too wet for too long, it brings different minerals concentrated into an area, and then it will dry, and then it'll get wet again. I believe that that's what modeling is. I think that it's poor aeration. It's similar to redox, is what it is, and it might actually. Is it the same as redox? I thought that redox was the lack of
It is
oxygen.
a redoxomorphic feature. Sometimes you'll find small molts of like iron concentrations or magnesium concentrations in a soil, and it'll almost look like a speckling. So you'll have like a lighter brown soil with like yellow spots in it. It's very interesting to see.
All right, great, thank you. And on my second question,
yeah, go ahead.
So I remember you talking when you were mentioning like the E layer that forests cause that. What is it about forests that lead to that happening?
So the reason that forests have this E layer, I believe it's because of the calcium carbonate. I could be wrong. I think that it has to do with the vegetation on above it, and the type of vegetation that is accumulating and therefore leaching. It also could be because usually forest ecosystems don't have this super thick A horizon. Robert, do you?
Yes, that's my understanding as well. I think the lack of disturbance also plays a factor because it allows that alluviation to happen. Yeah.
Right. And I do know that, and often I think the I think that it also has to do with that forests, not all forests, but a lot of forests usually receive higher precipitation. And because forest litter is, I think, acidic. I believe that forest
Yes.
litter,
Yes.
like needles, pine needles, that's pretty acidic. So I think that the precip in combination with that kind of will leach the uh, the minerals down, causing that like bleached looking layer.
All right, great. Thank you so much.
Of course. It looks like Shauna Ashley, you were next with your hand up.
Yeah, I also have two questions.
Of course.
So if sand has a lower porosity than clay, then why does it have a higher infiltration rate?
So the porosity is actually higher than clay's because it has those larger particles. It's going to have more airspace between them. You can think about it like if you put a bunch of like soccer balls in a fixed space, those soccer balls are going to have a lot of space between them. And the infiltration is going to be how quickly water can move through that space. So those soccer balls, again, they're going to have a lot of space between them, and that water is going to move through them quickly. Now, if you threw some like tennis balls and golf balls in there, that would be more like the clays and the silts. And so imagine a bunch of golf balls in that same container. Not as much airspace. The water is going to have a lot of things to move through, so it'll have a lower porosity, or sorry, a lower infiltration rate. I hope that's a good explanation.
I just thought like that finer textured soils have they have high, I mean, they have lower bulk density because they have more pores, right?
They
So
do. They have higher porosity. You're correct. The clay soils have higher porosity, although they're smaller particles. They have more surface area. Although sand has larger pore spaces, there's not as many. So it's because clay particles are so teeny tiny that they create so many pore spaces between those teeny tiny particles. And so the reason that clay soils are more, their porosity is higher. Sandy soils have higher infiltration rates because that water is not being held within that soil. It's moving through it so quickly because those pore spaces are big and it can't hold on to water nearly as easily. So it's kind of going right through it.
Okay, thank you. I also had one more question. So in an earlier slide, there was a BE layer, like capital B, capital E. How does that occur? Because that's like a layer of eluviation and illuviation.
I don't know where that one was. Let me see. A BE. So if you have it means that it's primarily a B horizon, but there's some E qualities to it. You're gonna see layers, profile layers that have multiple master horizons in the same one. But the first one that's listed is the predominant kind. You can't write a lowercase e next to it because lowercase e, that's a subordinate horizon, and that means moderately decomposed organic material, and that's just different than an E horizon. It's a B horizon that's a little bit E.